right, go ahead and have your homework out. Your textbook's open at page 144. You had just 4 problems to do for homework last night. 4 equations to solve. Good. Oh, okay, gotcha. I was assuming that this was where the homework started because I used this one. Gotcha, you were separating out. Gotcha. All right, we're good. With that. Gotcha. You just randomly interjected physics notes into the middle of the pre-cal. Yeah. Why, Jamie, that is such nice, neat, labeled work. Thank you so much. Quentin, lovely. I can find everything. All right.
What about us?
What about you? All right, number 5 on your homework. You were given that the cosecant or cosine of chi times the cosecant of 2 chi is equal to 2 times the sine of chi. And get my calculator out. I don't need it yet, but we will for 19, we said. First thing I noticed is I've got 3 different ratios, 3 different trig ratios, trig functions here. And generally, when there's multiple trig functions, class, we want to...
Sines and cosines? Oh no, isolate and...
Set it equal to 0 and factor. That's what we want to do. But I've got another issue. Not only do I have multiple trig functions, I've got single angles and a double angle. And anytime that's the case, I said we've got to do what, class?
Get rid of the double angle.
Get rid of the double angle by using the double angle identity. What is the double angle identity for cosecant 2 chi?
1 over...
He knows it's a reciprocal. It's like, wait a second, what is sine's double angle? I think it's on the back cover of your book, if I'm not mistaken.
2 sine, 1 cosine.
Yeah, it's on the back of your book.
Oh, it is?
Yeah, 2 sine, theta, cosine theta. But in this case, 2 sine chi, cosine chi. And again, this is going to be 1 over, but it's all going to be times cosine. So I'm going to go ahead and put the cosine chi up here, all equal to 2 sine chi. And I'm going to put the 2 sine chi class over 1. Now, it's very, very tempting right here to cancel away those cosine chi's. So tempting. But am I allowed to cancel trig functions, class? No. We set equal to 0 and factor instead. But I've got a bigger, like, I'm not even ready to set anything equal to 0 because I have a proportion. What should I do with this problem now, Chris?
Cross multiply.
To get?
4 sine squared, 2 sine cosine.
What about 4 sine squared cosine?
And then over cosine.
Equals?
Oh, equals cosine.
There we go. Okay, we cross multiply. The product of the means, which is 4 sine squared cosine, equals the product of the extremes, which is just cosine. And now we can set it equal to 0, class.
Move it over as a negative.
Move the cosine over as a negative, and now it equals 0. And now that it's set equal to 0, class, we can factor. And we can, of course, factor out a cosine chi to leave us with what, Jamie?
4 sine squared chi minus 1.
And, of course, we want to set each of these equal to 0. And we end up with 2 little equations here, Quentin.
Cosine equals 0. Sine chi equals positive negative square root of, or positive negative 1 over 2.
Good. You move the 1 over, divide by 4, take the square root of a fourth, that's positive negative 1/2. At this point, let me move this out of the way, sorry, gentlemen. At this point, we go ahead and solve, but there's something I failed to do earlier, and I just saw it. We've got a denominator right here, correct? And we know this, that nothing in the denominator is allowed to equal 0. 2 isn't allowed to equal 0. Well, duh. Sine is not allowed to equal 0, and cosine is not allowed to equal 0. So 2 little qualifiers, thoughts.
Cosine equals 0.
It says cosine equals 0, but it's not allowed to. So I'm going to rule that out right off the bat. Okay? So really all I've got is that sine is equal to positive negative 1/2. So that's going to cut down my answers that I need to find. What do we end up with for chi, anyone?
30 degrees, 150 degrees, 210 degrees, 330 degrees.
And there we go. And that's what we should have gotten for number 5. How many also had 90 and 270? Maybe you forgot that cosine could not equal 0. That's what we would have gotten there. Or excuse me, 0 and 1, 8. Yeah, 90 and 270. I was right the first time. But these are the answers we should have gotten. 90, 270 are extraneous questions.
I forgot to put the cosine as a reciprocal.
Oh, so you left cosine times 2 sine cosine. Gotcha, okay.
The cosecant, I forgot that 2 sine equals 2 sine cosine.
Oh, gotta have those identities memorized. Other questions, comments, feedback?
I had already moved over the 2 sine pi at the start, so I didn't see the proportion.
Well, you can still get it if you multiply everything by 2 sine cosine. That cancels all of this. That's where we'll get that same 4 sine squared cosine. And of course, anything times 0 is 0 anyway. So you'd actually end up with the same thing but reversed. But it would end up coming out to the same answers. Or should have come out to the same answers. Ethan, feedback? All right, let's take a look at the next one you had, which was number 8. I know this one was really straightforward. Cotangent 2 eta equals square root of 3. Is that correct? Okay. Mine originally didn't have that, and so I've got to change an edit in my book. Just want to make sure that that edit that I have is still applicable to what you have. Really straightforward, though I would put the square root of 3 class. And then ask myself, when is cotangent square root of 3 over 1? When is adjacent over opposite square root of 3 over 1? Class? 30 degrees. And notice it's not positive negative, it's just positive. So my 2 8 is going to be 30 degrees because it's positive in quadrant 1, and 2 10 degrees because cotangent is positive in quadrant 3. But it's a 2 eta. So what do I have to do, Ethan?
Double.
Go around. Boom.
We just have to add 360.
There we go. Go around again by adding 360 to also get
390 and 570.
There we go. But that's 2 eta. To finish the problem, I need just eta equals. So I'm going to take all these answers, Chris, and divide them all by
2
to get
15, 105, 195, and 235. No, wait, no. 280, yeah.
And there we go. How many have these answers? Good, Quentin. Ooh.
I had a couple of them.
I thought this was an easy one, frankly. I mean, that's all there is to it. Questions? I understand it now? You're scaring me. All right, next one you have is number 15.
Do we have a question?
Tangent squared alpha over cosine squared alpha plus secant squared alpha equals 16. Thoughts on what we might do here, Jamie?
We can change the tangent to sine or cosine.
I guess you could. That wasn't what I was thinking. I suppose you could.
You could turn the secant squared to 1 over cosine squared.
That's kind of more, because I already have a denominator cosine squared here. That's what I was thinking. It doesn't really make a whole lot of extra work, frankly. We already have to specify that cosine alpha can't be 0. You say, well, I thought it was cosine squared can't be 0. Well, yeah, but then you take the square root of both sides and it's cosine can't be 0. It's an easier way to think of it. So we already have this qualified statement anyway. Why not go that route? And then I can knock the fractions out really easily, Quinn, if I multiply everything by the LCD. Or I could consolidate it down to a single fraction and cross multiply. Either thing is going to give me the exact same answer anyway. So either way I work, either multiply everything by cosine squared or connect this all as one fraction and then cross multiply. Either way I get what?
16 cosine squared equals tangent squared plus 1.
There we go. If I multiply by cosine squared, I get tangent squared. Multiply by cosine squared, I get 1. Multiply by cosine squared, I get 16 cosine squared. Or, prior to the extremes is tangent squared plus 1. Prior to the means is 16 cosine squared. But now I'm staring at a tangent squared plus 1, and my identities are going off in my head here, Ethan. Hopefully they are in yours as well.
Tangent squared angle plus 1 equals Secant squared.
There we go. That just equals secant squared alpha. So we get 16 cosine squared alpha equal to secant squared alpha. I know I should be, I said equal to 0 and factor, but even if I said equal to 0, I wouldn't be able to factor. But there's another thought now going off in my head.
1 over cosine per secant?
Yeah, I mean, we did it once before. What if we did it again? What if we once again said 1 over cosine squared alpha equals 16 cosine squared alpha, and maybe again put it over 1. And by the way, I've already got this qualifying statement here, so it doesn't even make an extra qualifier. Let me erase this to give myself room to work to the left here. Thoughts on what we would do now, Jamie?
Are we going to cross over?
That's generally what we do with proportions.
So 16 cosine to the 4 alpha equals 1.
And now I'm ready to get my answer by itself. We've turned this not into a quadratic, but a quartic equation. And I showed this once before, a few lessons back. What you'd think is divide away the 16 and take the 4th root. But remember, I said you can't take a 4th root. We take successive square roots. So let's take the square root of both sides. What's the square root of cosine of the 4th class?
Cosine squared.
Cosine squared. What are the square roots of 1/16? Positive and negative 1/4. Then we'll take the square root again. Square root of cosine squared.
Cosine.
Square roots of 1/4.
1/2.
Positive negative 1/2. Square roots of negative 1/4.
Negative positive.
Positive negative I times 1/2. But imaginary? When is cosine imaginary?
Never.
It's not. Now, if you were to take the 4th root of both sides, you would get these two answers, but you wouldn't be able to account for the imaginary. And really, truly, in this particular problem, it wouldn't matter, because we're not dealing with the imaginary. But because we're going to get to imaginary and complex numbers later, I wanted to review the double square roots as opposed to a straight 4th. Anyway, we should get to this point. And now it's easy. When is cosine adjacent over hypotenuse? What over 2? 60. And so we need all the 60s. So my 4 answers for alpha.
60.
And there we go. Now this one, admittedly, unlike the last two, in my opinion, a little more challenging because you had to have some stick-to-itiveness, right? You got the 1 over cosine squared, and then multiplying by the LCD, and then another Pythagorean, and then another reciprocal, and then another cross multiply. So a lot of work went into it. Did anyone get this? All right, great job.
Shorter, actually.
You found a shorter way. Okay, what was your shorter way?
The tangent squared alpha plus 1, I turned that to secant squared alpha.
Ah, so right here you went secant squared.
And then I changed cosine squared alpha to secant squared alpha over 1.
You mean, okay, you initially 1 over secant squared, but then you multiply by the reciprocal and got secant squared over 1 to go straight to secant to the 4th equals 16.
And then I divided away, or I took the square root once, and then I took the square root again.
And then you would get the exact same answers. All right, so yeah, that is true. That would be quicker. I wish I thought of that. I didn't see, for some reason, I didn't see the Pythagorean here. I didn't see it until it came up down here. But that would have saved a little bit of time. All right, good.
Are you smarter than a 12th grader?
I don't know, maybe not. All right, way to go, Quentin. Questions on this? All right, Quentin's like, I'm going to send this YouTube clip to all my college admissions people. And see, this is why you need me. All right, questions on this. Great job, Quentin. Show off. All right, let's take a look at the last one.
Is it April Fool's or something? Because that was shorter, not longer.
I know. What is this? He just usually does things the long, hard way. All right.
It's definitely chicanery.
Good word, good word. Is that on your vocab list?
It was.
Yeah, it's chicanery anyway. It's a long A sound, but whatever.
Chicanery.
Chicanery. It sounds like you're putting something in a can.
Chicanery. What did I say?
You said chicanery. It's chicanery.
It is.
All right, number 19 was easy, but you had to use a calculator. First of all, I'll put the 3 over
2.
1.
Wait.
1. And I'll ask
That's not
myself,
what I
When it's secant, hypotenuse over adjacent, 3 over 1. And in a special triangle, it's not. But the hypotenuse can definitely be 3 to a leg of 1. Absolutely, right? Hypotenuse bigger than adjacent, yes. But we have to pull out our calculators. Here's the problem. I can't necessarily take the arc secant. So I'm going to have to think of this as the cosine is 1/3. And I'm going to take the arc cosine of both sides to get that 2 theta is equal to the arc cosine of 1/3. And what do we get for our angle? 70.528, blah, blah, blah. Now, I would put that in the memory of the calculator. Because we don't just have that angle. Cosine here is a positive, right? So it's positive in quadrant 1, so it would be 70.5 degrees. And in quadrant 4, so 360 minus memory 1 gives
289.47.
about 289.5 degrees, okay? Wouldn't hurt necessarily to put that in memory 2. Now, if we're smart, and we plan carefully, those of us who don't have unlimited memories, Ethan's got a lot, we only have 3, we've already used 2. Here's my thought. Well, you don't have to have more memories if you're smart. I know both of these angles, to get theta class, I'm going to have to cut them in half. So while this is actually on the calculator screen, let's go ahead and divide it by 2 to get,
144.7.
I'm going to round that to 144.7. All right, let's also go back to memory 1, and let's go ahead and divide that in half.
35.264.
Which will round to 35.3. All right, now then, let's go back to memory 1, and let's go ahead and go around again. So let's take memory 1 and add 360 to get
430.5.
But I'm not going to waste a memory. I'm immediately going to divide it by 2.
215.264.
Oh, so rounded 215.3. And then I'm also going to take my memory 2, recall 2, add 360 to that, and then immediately divide that by 2, so I don't have to use a memory on that either.
324.7.
And so we only using 2 memories to get these 4 answers. I didn't have to do a whole lot of the add 360, put that in memory, add 360 to that, put that in memory, divide this memory by 2, divide that, right? If you're smart, you can get by with the fewer memories, and that's really the key. Plus, it's easier to do it that way. You have less keystrokes, which I'm lazy, so I'm actually counting keystrokes. Anyone get these answers?
Unfortunately, no.
Questions?
Because I forgot about calculator bar.
I even mentioned it in the homework. You're going to have to use a calculator because it's not going to be a special triangle. All right, questions on how to use the calculator? Anyone need that re-explained what to do if it's weird like this, where it doesn't come out evenly?
So, yeah.
Okay, so let's just say, for instance, we've got the cotangent of, I don't know,
643.
of tau is, let's say, 4/5. Let's say -4/5, just to really mix it up here. Well, that's not a special triangle, but Jamie, it's entirely plausible that the 2 legs of a triangle could be 4 and 5, correct? The problem is you can't take arc cotangent. So what we're going to have to do is turn this around and say, well, that means that the tangent of tau is -5 to 4. And then we'll take the arc tangent of the -5 to 4. Or rather, let's just take 5 to 4. Okay, negatives make things messy. So let's just do 5 to 4. Take the arc tangent. What is our reference angle?
51.34.
All right, we're going to put that in memory 1. Okay, but it's negative. So that means we're only dealing with quadrants 2 and 4. So we're going to do 180 minus that memory. I didn't save it in the memory. 5 over 4 arc tangent. Now save it in the memory. Okay, so 180 minus recall 1 puts it at 128.7. And then quadrant 4 is 360 minus recall 1.
308.659.
So 308.7. Now, if this were a 2 tau, I would have put this in memory 2. I would have put this in memory 3. Then it would have added 360. Well, it would have probably divided by 2, divided by 2, add 360, divide by 2, add 360, divide by 2. Get the answers that way. Right? Does that make sense? Again, you're not going to see it often. It's generally we're working with special angles, But when we do, I want to make sure we're able to handle that. Questions on the homework at all? All right, you're in your books already, page 145. Copy down number 27, if you would, please. And Ethan, this one bears a little resemblance, at least initially, to what we had in the homework on that first problem. So, Ethan, what do we do?
Number 7?
Number 27.
Oh, I thought I heard 7.
Sorry. We got a cosecant 2 sigma equals 2 tangent sigma.
Oh yeah, so 1 over 2 sine cosine.
Good. 1 over 2 sigma cosine sigma. Like how he just bails out, it's like just this angle instead of Greek letter.
It works.
Equals, and what do we suppose? Should we just leave 2 tangent, or maybe another thought there, Chris?
Sine over cosine.
Yeah, let's do 2 sine over the cosine. Now, last time I waited too long. I really need to do this as soon as I create a fraction. Let's go and specify some things, class.
Sine cannot be 0, cosine cannot be 0.
So, all right, sine and cosine, neither one is allowed to be a 0. All right, now what, Quentin?
Cross multiply.
Excellent. When you see proportion, just go straight to the cross multiplication. What we got?
2 cosine sigma equals.
Where'd you get 2 cosine sigma? Oh, careful.
Oh.
You did 2 tangent is 2 sine over 2 cosine. Careful. It's 2 sine over 1 cosine. That's where the 2 came from.
Yeah.
Careful.
Cosine sigma equals 4 sine squared sigma cosine sigma.
All right. Cosine equals 4 sine squared cosine. All right. Then what? Back to Chris.
Cosine equals 0.
Which side?
Right side.
Yeah. Okay. We could do that. I'm lazy. I'd rather only do
cosine
one.
over. That's what I'm saying. That's what I meant. Bring
Left
it
side.
back.
Bring it to the right, set the left side 0. I gotcha. So that means we're going to have the 4 sine squared cosine minus the cosine. Or if we're really lazy, I just cross this out, put 0, and put minus
And
cosine,
you
which
can
would have been a lot
pull
easier.
out a cosine.
Good.
And then you can get your, oh sorry, it'd be 4 sine squared by this one. Then you can get your 2 equations, so cosine angle equals 0.
Cheater. Don't follow after Ethan. Horrible example. Sigma.
So then you have sine equals positive negative 1/2.
All right, Jamie.
And let's see, we cannot be crossed out the cosine equals 0. And then the sine is also over hypotenuse, so that means that it's 30 degrees. And
Yes.
so we'll have, and it's going to be all for quadrants, so we'll have 30 degrees, 450, 210, and 330.
And there we go. All right, questions on this? Feel better about it now that you've done a second, because this is very similar to how number 5 went down. Slightly different effect. Almost the exact same problem. If you divided both sides by a cosine, which technically you're not supposed to, it would be the same problem. Yeah, I was like, man, that's really similar. That's why. Now, there's something new I want to, I say new, we've done it before, but we haven't done it often. I want to show you a few examples. Number 9, copy it down. And something that's available to us if we need it, but it's kind of a last resort. As we look at number 9, we've got the sine of theta plus the cosine of theta equals 1. If that were sine squared plus cosine squared equals 1, duh, that's an identity, right? That's always true. But it's not squared. And that's a problem. Because I have multiple trig functions, but even if I set it equal to 0, I can't factor anything. I can't even manipulate this into anything else. And if there were squares, I could, but they're not squares. So if you really need squares, and you ain't got squares, remember with a radical equation, We said we could isolate the radical, and then we could square both sides. If you do that, you run the risk of creating extraneous roots. You remember that? But we may have to do that with our trig ratios if we really need them to be squared. Here's a strategy tip, though. Don't have multiple trig functions together. Isolate one of them. So I would recommend bringing one of these two guys to the other side first, before we go squaring. All right, so let's go and bring the cosine over as a negative cosine, and now let's square both sides, with the understanding that when we get our answers, we may have created extra answers by squaring, because we're making more sines and cosines than we started with. We're going to have to check all of our answers with the original. Well, obviously when you square a sine, class, you get
Sine squared.
sine squared. But when you square a binomial, like we're doing here, 3 steps, class.
Square the first, square the last, multiply and double.
When we square the first, that's just
1.
When we square the last, that's just
Cosine squared.
positive cosine squared, because you always get a positive when you square. What do we get when we multiply and double?
Negative cosine.
Negative 2 cosine theta. Good? Now, I now have turned this into a quadratic, and with a quadratic, we want to set it equal to 0 and factor. But again, if I bring this over, that's causing a little bit of a problem, isn't it? Unless I first transform sine squared somehow into a cosine. How does sine squared turn into a cosine?
Pythagorean theorem.
Pythagorean identity. What is the Pythagorean identity for sine squared?
Sine squared minus 2 sine squared equals 1.
How about sine squared plus cosine squared equals 1?
What did I say?
Sine squared minus 2 sine squared equals 1. So sine squared plus cosine squared equals 1. So what is sine squared, class?
1 minus cosine squared.
1 minus cosine squared equals 1 minus 2 cosine plus cosine squared. All right, thoughts?
Cosines do not cancel.
The cosine squareds do not. Rather, this little one should move over as a positive cosine squared to give me 2 cosine squared.
Ones are going down.
The ones, however, will cancel. So I'm left with the 0 that I wanted minus 2 cosine.
Move the
1 out of 2 cosine.
Good, don't move anything over, factor. We've got our quadratic, it's a complete quadratic. I have a squared and a first, even though I don't have a constant term anymore because they canceled. But I can still factor out a 2 cosine. Leaving me with, in parentheses,
Cosine minus or theta minus 1.
cosine theta minus 1. I appreciate the effort there, Ethan. I know it was hard for you. And so we end up saying that cosine theta equals 0. And cosine theta equals
1.
I'm going to put both of these over 1, and for the 0, I'm going to put
2. Positive negative.
positive negative. You could say over 2, over 1, over 2, doesn't really matter. Over anything is still 0, which we could say is over 1. All right, so when is cosine adjacent over hypotenuse is 0 over 1?
90.
At 90, or since it's positive negative, we'll say 90 and 270. When is cosine 1 over 1?
45. No.
Adjacent over hypotenuse. At 0. Not 0 and 1/8, correct? Okay, but we've got to go back to the original problem and check every one of these. Notice we don't have excluded values. We don't have fractions, but we do need to check and make sure I didn't make up an answer that should not exist. The original problem said sine plus cosine equals 1. You can use your calculator for this. The sine of 90 plus the cosine of 90. What does it equal?
1.
We're good. Sine of 270 plus cosine of 270.
Negative 1.
Oh, that's extraneous. All right, the sine of 0 plus the cosine of 0.
1.
All right, so that one checks. So my only answers are the 0 and the 90, not the 270. But do you see how by squaring, I opened the door to being able to do something where before, I mean, you're just stuck. What can you do? Nothing. Squaring things. Again, I don't recommend it because you have to check and I hate checking, okay? But if it's your only option, and it was on number 9. Let's take a look at number 12 next. Sine gamma plus 2 cosine gamma equals 2. I feel like I did a really good gamma right there. Props to me. I've been practicing for a dozen years. I should be getting better. Once again, do you see that there's really not much to do, right? I mean, setting it equal to 0, I wouldn't be able to factor, but if only they were squares, I could do something. So once again, we want to isolate one, square both sides. Not isolate the radical, but isolate a trig function, square both sides. Remember, I used to say isolate the ugliest radical. Like if I had the square root of 3x minus 2 plus the square root of x equals 5. I say this radical's uglier. Isolate that one. Get it all by itself, then square both sides. Well, of the trig functions, there is an uglier one. Which one's uglier? The 2 cosine. So let's isolate that. So let's move the sine over. So you get negative sine gamma. And now let's square both sides. On the left.
4 cosine squared.
On the far left. Right. All right, on the right, we have
4 plus sine squared minus 2 sine squared.
well, not 2 sine squared, just negative, oh, careful, multiplying double.
4 sine.
Negative 4 sine. All right. Now, we either need to turn the cosine squared into sine, or we need to turn the sine and the sine squared somewhere into cosine.
Cosine.
Yeah, because this you could turn into a cosine, but you can't do a thing with a regular sine. This can change. So let's turn the cosine squared into
1 minus
all equal 4 minus 4 sine gamma plus, that's a horrible gamma, sine squared gamma. All right, then of course we need to distribute to get
4 minus 4 squared gamma.
equals 4 minus 4 sine gamma plus sine squared gamma. Careful not to be in too big of a hurry. Where you say, ooh, there's a negative 4 and a negative 4, or, well, one's a negative 4 sine squared, the other's a negative 4 sine. They're not the same, don't cancel them. But I can cancel 4s, the plain old 4s, the constant terms. Instead, we want to send the negative 4 sine squared over as a
positive.
to get how many sine squares on the other side now? 5 sine squared. And then I still have this lonely negative 4 sine gamma that, doesn't have any like terms. Well, it's set equal to 0. Now I can factor. How do I factor this polynomial?
4 out of 4 sine.
Well, there's not a 4 common, but there's at least a sine common, right? I can at least factor out a sine gamma, and it'll leave me with
Sine minus 1.
minus 1?
Minus 4.
Minus 4. Ethan, you with me? Are you strangely quiet? And your desk is sliding forward right in my way. So that means that the sine of gamma class equals 0. How should I write that?
Over 1 plus or minus.
There we go, positive negative 0 over 1. And the sine of gamma equals,
Negative 4, positive 4.
which will be quadrants 1 and 2. And yup, we're going to need a calculator for that reference angle. Oh, can it even be 4 over 5?
Yes.
Yeah.
Yes, leg over hypotenuse, yes, can be 4 over 5. Good news, if it doesn't, your calculator will say error. So you can kind of cheat your way out of it. What's the reference angle?
53.1.
All right, let's put that in the memory. And then in quadrant 1, of course, it is the 53.1 degree angle. And in quadrant 2,
126.8.
so 126.9.
Yeah.
Let's put that in memory too. say, why do we need it in the memory? Because remember, when you square both sides, you risk creating extraneous roots. All right, let's come back up here. This, fortunately, is special. 0 over 1. When is sine 0 over 1?
0 degrees.
0. And positive negative means both 0 and 180. So 4 possible answers. 1 or more may be extraneous. Let's go back to the original equation, and we can use our calculator to check. Yeah, okay, good. I've got both angles in memory. I didn't forget this time. Let's start with the easy one, though, 0. So take the sine of 0 plus 2 times the cosine of 0. Does it equal 2? Sine 0 plus 2 times the cosine of 0. Yes. All right, let's do 180. Same thing. Sine of 180 plus 2 times the cosine of 180.
Sine of 180 plus.
Sine of 180 plus 2 times the cosine of 180. And does it equal 2?
Yeah, it's negative.
Negative 2. Okay, so the 180 is extraneous. Let's try the 53.1. Sine of, and use the memory value, so sine of recall 1 plus cosine of recall 1 times 2, does that equal 2?
Yes.
That's going to be really close to 2. I've got it slightly bigger than 2. Let me try this again. So recall 1,
I got 2 exactly.
sine plus recall 1 cosine times 2 close parentheses equals. I don't know why my calculator should be exact. I'm not sure what my problem is.
I got 2 exactly.
Okay, all right. I'm not sure what happened. I may have bumped something and messed it up. All right, so we're saying this one checks. Let's try the 126.9. So recall 2 sine plus and what does that come to?
0.4.
Negative 0.4. Okay. So 0 and 53.1 degrees work, but not the other two. Questions on that? Let's see, that was number 12. Let's drop all the way down to number 22. Number 22. And we're back to gamma for a second straight problem.
I think third.
What's the problem?
I think it's the third problem.
In a row? No, we had 9, 12, and 22. 9 was theta. But yeah, we use a lot of gamma. All right. Here we literally have a radical equation. But that's not why we feel like we need to square something. It's because, once again, we got a plain old sine, a plain old cosine. By the way, other clues, I know they keep giving you sine and cosine. Cosecant and cotangent in the same problem would imply you would want to square, because those are Pythagorean with each other. Tangent and secant in the same problem with each other would imply you probably want to square both sides. Here, which is the uglier radical?
The negative square root 3.
The negative square root of 3 cosine, right? So let's isolate that. Thoughts?
Minus the sine.
We can either subtract the sine over, or if you didn't want the negative at all, you do the double switch. Bring the 1 over as a negative and send that over as a positive. Really doesn't matter. So I'm going to go ahead and bring the sine gamma over. Just remember, when you square a negative, you get a positive. So sine becomes positive. When you square the square root of 3, 3, because when you square a square root, you get the radicand. Good, Chris. And we square the cosine, of course, that's cosine squared. Questions on that first step? And then on the other side, of course, 3 steps.
Multiply first.
Square the first, square the last, multiply and double. All right, what do we get? Ethan.
You should square the first square line. 1 sine squared gamma.
Always positive when you square.
2 sine gamma.
And what SIGN?
Positive.
Here negative. So when you square the first positive one, square the last positive sign squared. When you multiply and double, whatever this sign is what this will be, because positive is negative. 1 times 1 is 1, doubled is 2, and of course we'll keep the sign. But what do I need to do next, Ethan?
Factor out the sine.
Well, it's not. I don't have a sign everywhere to factor out. This is the misfit. Let's turn it into a sine.
1 minus sine squared.
There we go. Use that Pythagorean identities Chris just said.
Sorry, I was taking
Chris is like, ooh, highlight reel. I hadn't thought about that possibility. Hey, there's the upside of being in a YouTube class. Because what college is going to check it on their own? But if I send it to them, you know, it's like, so my bad moments they'll never see, but I can make them hear my good moments.
I wonder if that would actually work.
I don't know. I really don't know.
It's like a sports.
Because they can't actually see you. All they hear is your voice, and I don't know.
It's like a sports mixtape.
Yeah, like you're in recruiting, right? You see, I watch those, especially during the downtime of football, where I'm like, there's nothing going on. Who are the top recruits? Let me watch their highlight reels because I got no other football to watch right now. It's a sad day when football season ends. All right. Now what, Jamie?
Distribute
To get
3 minus 3 sine squared. Yeah.
And again, the pattern is kind of consistent here. You keep seeing the same kind of thing. It's a little bit different numbers each time, the same kind of thing happening every time. Quentin? Okay.
Negative 2 equal, or, yeah, negative 2 plus, negative 2 minus 2 sine gamma plus 4 sine squared.
And if this troubles your soul, it's because we're used to seeing a descending order here. We've got the ascending order instead. That's okay. I can flip it around easily enough. But here, it's not a common factor. Well, I guess I could actually divide everything by 2. There's nothing wrong with it, because numbers you can divide away. It's just trig values you can't. So I could flip it and divide a 2 out. Let's see if Ethan is smart enough to do both things at the same time.
Okay.
College highlight reel time. Here we go.
2 sine squared gamma. I didn't see that. Plus 2 a sine gamma.
Okay, so minus sine gamma.
I was looking at and minus 1.
There we go. And now what, Chris?
Foil.
Yeah, backwards FOIL, right? Factored up. 2 sine squared.
2 sine, 1 sine. And it's going to be positive, negative, 1, 1.
And does the outer inner check? Or do we need to flip things around? Or do we need to use the quadratic formula to have it help us?
Check.
All right, so 2 little equations then, Chris.
Sine equals 1 over 2. Positive, negative, 1 over 2.
Move the 1 over as a...
Oh, negative 1 over 2.
There we go. And then...
Positive 1 over 1.
All right, when sine a half class?
60.
You're 30.
30. When's it negative?
3 or 4.
3 and 4, so the 30 and 3 and 4.
2 tans is 30.
All right, and when is sine 1 over 1?
90.
90. And only 90, not 270, because it's not positive, negative. But it's possible that although I only have 3 answers, one of them could be extraneous. Come back to the original. This is fun. You know what? Let's do this first. Let's start with this. Let's start with the cosine of 210 times the square root of 3, and then hit your positive negative button to change the SIGN. So 210 cosine times 3 square root, change the SIGN. Should have a positive 1.5. And then add the positive sine of 210 plus 210 sine equals.
Works.
All right. Let's try 330. Same thing. So 330 cosine times 3 square root, change it to a negative, plus 330 sine equals
Negative 2.
negative 2. All right. Try the 90. 90 cosine times 3 square root. I change it to a negative, plus 90 sine equals.
1.
And that one checks as well. So the 90 and 210 are good. It's just the 330 that's no good. Questions? do you see the times when to square? That's the other thing, is not just knowing how to do it, but to spot when it's necessary to square both sides. Very rarely. Again, I know we did 3 in a row, but that was to teach it to you. You're not going to use this often. This is a, nothing else is going to work, let me square both sides. Questions? All right, we don't have a whole lot of time, sadly. Let's look at 23 very quickly. Because we do have something in 23 that we haven't seen in a little while, and that's your half-angle identities. Now, the thing that's annoying about the half-angle, remember, is they become radicals, right? But if you're looking at number 23, there's something that's going to make the half-angle not quite as bad.
Squared.
The fact that it's squared, right? So cotangent squared half lambda is equal to 3. So that's the saving grace. What is, ignore the square for a moment, what is the cotangent? Okay, what's the tangent half angle?
There's like different ones.
There's 3 of them. Well, we're going to flip it. Let's just go with the radical because it's going to be squared anyway.
1 minus cosine over 1 minus cosine. I mean, 1 plus cosine.
Yeah, you remember this? Positive negative square root of 1 minus cosine over 1 plus cosine, but that's tangent. Cotangent is the reciprocal. So it's going to be
1 plus cosine over.
Right, 1 plus cosine over 1 minus cosine, and technically it'll be the square root, right? But that's going to be squared, so it's going to knock the square root off anyway. Does that make sense? And again, since this is not a verification, I don't have to show all of that. I can do that in my head. That's why I love chapter 7. All equal to 3, or 3 over 1, so that we can cross multiply to get
3 minus 3 tangent.
ooh, cosine.
What is it?
Oh, and that's not so bad. I got a cosine. You're doing this with me on your paper. Oh, people, if you've been doing this with me, number 1, you lose a study resource. Number 2, you lose the practice. So don't just watch. Make sure you're doing it with me. I got a cosine on both sides. Thoughts? Well, but it's the same function, right? It would be like if I had a 3 minus 3x equals 1 plus x. I don't need to set it equal to 0. It's not a quadratic, and it's not like I've got a second letter in there. I just need to get rid of the little x.
So move the 3 cosine.
Yeah, make that a positive 3 cosine. So for that matter, let's move the 1 over as a negative to get
2 equals 4.
yeah, super easy. And then when we divide away the 4, we'll get cosine equals half. Oh. So again, on the surface, you look at it, it's like, oh my goodness, that's objectively terrifying. But it's really not that bad. When does cosine half? 60. Reference angle is 60, but we're in quadrant 1 and 4. So 60 and 300. Now, I guess the only qualifying thing is cosine cannot be a 1, right? That's the only restriction. Cosine can't be a 1, but it's not a 1, it's a 1/2. I didn't square both sides, right? The square was already in the equation, so don't need to check those answers. They will work out because they don't violate this 1 restriction, and we're good to go. Questions on this? Let me give you just 2 to do for homework. I know it's a Wednesday. I normally wouldn't, but I think we need the practice as we head into tomorrow. Let me give you page 145. This is going to be a little bit easier. I saved these for you. Page 145, let's do 33 and 35. 33 and 35. So homework for this evening, just 2 problems. Page 145, 33, and 35. We'll be taking a look at that in our next lesson and finishing up this section on trig equations. Have a wonderful rest of your day, and you are dismissed.